So how do we know whether or not a relation, in this case sets of ordered pairs, are a function or not? What are we looking for? How do I know if something is a function? How do I know if something is a function? How do I know if a set of ordered pairs is showing me a function or not? What am I looking for there? Domain. What about the domain? Domain is x, range is y. I like that. We can work with that. So if I were to, say, draw out my domain, my inputs, and my range, my output, what are the things that would go in the domain? Which pieces go in the domain? The first number in each ordered pair, the first number in each set of parentheses. So what numbers should I put in there? -1, 3, 5, and 7. What about in the range, in the output? What numbers should I put over there? -5, +5, 7, and 11. This thing that I've drawn out over here is called a relation map. I put all my domain pieces in one bubble. I put all my range pieces in another bubble. And then I'm going to use arrows to show which piece of the domain goes with which part of the range. So I want to draw an arrow from -1 to what number? -5. From 3 to what? From 3 to 5. From 5 to 7. And from 7 to 11. Every piece of my domain goes to what? Goes to an output value. Do we have any piece in our domain that goes to more than one thing in the range? No. Then it is a function. If every part in my domain goes to one output and only one output, it is a function. So what do we think about number 1? Function or not a function? Number 1 is a function. Let's look at number 2. Let's try the same kind of thing. I'm going to do a relation mapping. So I'm going to draw out my domain, my inputs. What kind of numbers should I put in the bubble for the domain? 0, 4. I already have 0 there, so I don't put it in twice. So 0, 4, and 3. I don't repeat any numbers when I do this. I would just draw more arrows if anything repeats here. And then what would I put in the range bubble or in the output bubble? 8, 7, 9, and 0. All right. Let's draw our arrows. 0 goes to what? 0 goes to 8. 4 goes to 7. 3 goes to 9. 3 goes to 9? Yeah. 0 goes to 9, right? And 3 goes to 0. Look at this right here. I want to focus your attention on this thing that just happened. 0 went to two different numbers, right? So we had one piece from our input, but it went to two different places in our range. 0 went to two different outputs. That is not allowed. If a piece of my domain, if a piece of my input goes to two different outputs, then it is not a function. So number 2, because we have this repeated input here with two different outputs, that means that this is not a function. If it had said 0, 8, 4, 7, and then 0, 8 again, that would be okay. I can repeat an input as long as it goes to the same place it did before. If I repeat an input and it all of a sudden goes somewhere else, it is not a function. Did you have a question, Jaden?
Does it work either or?
Does it work either or way? Good question. Good question. Let me draw another example here. So if this was my input, and this is my output, and the numbers that I have in my input, I'm going to be real creative here. 1, 2, 3. And I have 7 and 10 over here. If 1 goes to 7, and 2 also goes to 7, that is allowed. This is allowed. This would be a function. But we say it would not be 1-to-1. Does anybody remember first semester when we talked about 1-to-1? Does that phrase sound familiar at all? Yes. So in order for it to be a function, my input has to go to one spot only. Every time I see that same input, it's got to go the same place it did before. As long as that's true, it's a function. Anytime I have an input that goes one place one time and some other time it goes somewhere else, it's not a function. If I have more than one input value that points to the same output, it is a function, but we say it is not a 1-to-1 function. When I draw these things, when I graph them, things that are functions are going to pass the vertical line test. I can take my pencil back and forth across that graph, and it's only going to cross my pencil in one spot at a time. That would make it a function. To check to see if it's a 1-to-1 function after I know it passes my vertical line test, I would turn my pencil the other way and I would make a horizontal line. If it would not pass this direction, then I would say it's not 1-to-1. What'd you say? Oh, thank you. Hello. Oh, thank you. That's for you. And Elena. That's for you. And Chloe. We'll talk a little bit more about functions and 1-to-1. But today our big focus is going to be on something called inverse relations. Page 307 in your book for me. Big takeaway from today. When you see, hear, or read the word inverse, the word switch needs to pop into your head. Inverse, when you see, hear, or read that, I want the word switch to pop into your head. When we are talking about inverses, my x's and my y's are going to switch. So if I had an ordered pair that looked like this, it was A and then B. The inverse of that, I would take and switch them around. This is the inverse, and it is switched. We are going to learn and talk about 3 different ways to find out or to find inverses. One of them is just as easy as this. The first way that we're going to do this is we will just straight up switch x and y in an ordered pair. Do you need a packet? Okay. Switch x and y in an ordered pair, which is what they're describing right here. Like I said, we're going to talk about 3 ways to find an inverse. This is one of the ways we can find an inverse. If they give us ordered pairs, we just take whatever x is and whatever y is, and we make them trade places. And we do that to every single ordered pair we have. We make the x and the y switch places. Make our x and y switch places. We're going to practice that on the first example here. If I have 2 functions, and they are inverses. Do you guys remember yesterday when we learned how to compose functions together? I took one function and I stuffed it inside of the other one, and then we simplified. We used 2 different colored pencils for this. If I compose 2 functions together, and they are inverses, then they will make the identity function. What that means is that when I do f of g of x, I'm going to get just x back. When I do it the other way around, g of f of x, I would get just x when I simplified it. If that's true, then they are inverses of each other. Find somewhere in the margin or in your notes to jot that idea down. It's going to be really important. We will practice that idea tomorrow, but I did want to talk about it right now. If 2 functions really are inverses of each other, then I can put them together using that new operation that we learned yesterday, and I would have like terms to put together and things would cancel out so that I have just x left over. Not all functions have an inverse. If I have a function that fails the horizontal line test, then we have to do something called restricting the domain. I want to come in and practice doing some of this. Let's look at example number 1. If you look down at the bottom of the page, example number 1. Do you want to snap a quick picture? Do you need to snap a quick picture? Okay. They have this graph for us right here. Do you guys see that picture down at the bottom of your page? I want to look at the ordered pairs that they used. Here's 1 point. What's the x part of that ordered pair? 2. What's the y part? 4. I want to write the inverse ordered pair. You're going to have to write this down on the next page because for whatever reason they split this over 2 pages in your book. One of the other teachers here says that the people that put the book together, they made a choice. I don't know why they made this choice, but they made a choice. How can I take the ordered pair 2, 4 and write the inverse ordered pair? What do I need to do to the x and the y parts? Switch them. So the first part is now going to be what? The first part is now going to be 4, And the second part of the ordered pair will be 2. So my ordered pair becomes 4, 2. On the graph that you have at the top of page 308, I'm going to plot that point here, 4, 2. They have the same triangle there, but I'm going to plot that point, 4, 2. What about for the next ordered pair? Here they have B as negative 3, 2. How do I write down the inverse? 2, negative 3. I'm going to go plot that point too. 2, negative 3, right down here. And what about for the last one, the point that they have labeled C? 1, 4. All right, let's go plot that point. 1, 1, 2, 3, 4, right up here. Once you get all 3 of those points plotted on there, our inverse points, our switched points, I want you to connect those dots to make a triangle. What do you notice about our new triangle compared to our old triangle? It moved it. How did it move it? How would you describe the way it moved it? It flipped it. It almost looks like it rotated or reflected it, right? I want to look at it. Because like if it was a rotation, it would just be spinning like this. Did they take this triangle and reflect it down over the x-axis? That's not what I'm seeing. Did they take this triangle and reflect it this way over the y-axis? No. But it is a reflection, because you guys agree it looks like a very similar triangle. It's just somehow different on the page. Look at this diagonal line right here. If I were to fold it on that diagonal line, would it match up with itself? If I were to fold this on that green diagonal line, like this, now it matches up with itself. This is a reflection over the line y equals x. That's another way that I could find an inverse. So the first way that we had to find an inverse was to switch x and y in our ordered pair. We just practiced doing that. This line right here in slope-intercept form is y equals, it has a slope of 1, rise 1, run 1, rise 1, run 1, and it has a y-intercept of 0. So this is y equals x. That green dashed line that I drew is the line y equals x. So the other thing that I can do to find an inverse is reflect the original graph over the line y equals x. So that's the second way that we have. First way I have to find an inverse, if I have just a whole bunch of ordered pairs, I can take each of those ordered pairs and flip x and y, switch x and y, switch x and y. If they give me a graph, I can take that graph and I can reflect it over that diagonal line. So I could fold my graph on that diagonal and I could trace through. The last way that we're going to talk about today, and we'll do a couple examples with this. If they give me an equation we will switch x and y in the equation. Then we will solve it for y. These are the three ways we have of finding an inverse. I like it when they give me ordered pairs because it's easy. I take x and y, I switch them. I take x and y, I switch them. I take x and y, I switch them. I have my inverse. In example number 2, we're going to practice that third way where they give us an equation, and we're going to switch the x and the y. Let's look at example number 2. So they broke it out into 4 steps here. Let me actually copy that down onto the page so that we take our directions with us. They broke this down into 4 steps for us. Because in mine I say we switch x and y, but look what they gave us. I have f of x equals 3x plus 2. If I'm supposed to switch x and y, where's y? Look right here. First thing I'm supposed to do is switch x and y, but where's y? It's not there. Y is not there at all. F of x is called function notation. And function notation means the exact same thing as y. So when they give me an equation that has function notation in it, I'm like, Ms. Bolt said to switch x and y. There's not a y in the equation, but they're using something else that means the same thing as y. So the very first thing we are going to do is we're going to take that out, and we're going to replace it with a y. So rewrite the function, replace f of x with y. If I have it written like this right here, do you guys see how they took the f of x equals and they made it a y equals instead? That's all they're going to do to it in that first step. Now do you see x and y in the equation? Yes. Now can we follow my first step here? We're going to take the x and the y and we're going to switch them. Just the letters. No numbers, no operations, no exponents, no nothing will move, just the 2 letters switch places. So instead of y equals, I'm going to see what equals? X equals. Yes, x equals 3 what? 3y plus 2. X equals 3y plus 2. Take the x and the y and switch them. First thing you have to do is make sure you can see y in the equation. Then we take the x and the y and we switch places. Then we're going to solve for y. What does it mean to solve for y? What does it mean to solve for something? Get y by itself. Get y alone. So I'm looking at this right here. I want to get y all by itself. Which piece do I need to get rid of first? The 2. How do I make a 2 cancel out? Subtract it from both sides. So I'm going to minus 2 here. And I'm going to minus 2 over here. So my 2 is going to cancel on that side. And over on the left, I'm going to have x minus 2. They're not like terms, so I can't combine them. X minus 2 equals 3y. Is this y all alone? No. What do I still need to get rid of? The 3. How do I get rid of that 3? What operation? Division. So I'm going to divide by 3 over here. If I do it to one side, have to do it to the other side. So I'm going to have to come over here and divide this side by 3 also. So my 3's cancel out here. And over on the left, I have x minus 2 divided by 3 equals y. Very last thing that we do you remember how I started off with function notation at the beginning? Started off with f of x. Once I've gone through this process and I've found the inverse, we are going to replace y with something that looks like f of x, but it's got one extra little piece. What does it have that's different than what I started with? It has that little exponent of a -1. This is called inverse function notation. You doing okay, Taylor? Okay. Inverse function notation. So instead of a y equals in my final answer, I'm going to have f with a little -1 up here, and then an x inside of parentheses. That's going to take the place of the y. F inverse of x equals x minus 2 over 3. And if you look in this picture right here, do you see the blue line that they have that's kind of almost up and down? That's the original function that they gave. That has a y-intercept of 2 and a slope of 3. That's my original function. Do you guys see that light green one? That's my inverse function that we just found. Look what happens if I draw in that diagonal line again. Can you guys see how the original one is a reflection over that diagonal line? Oh, be quiet. The original function is a reflection over that diagonal line. Y equals x. We're going to practice finding one more inverse together, and then you guys are going to have the remainder of the time to get started on the homework. Homework is not due until Thursday. So you have today and tomorrow class to learn the material. So we're just finding inverses with today's lesson. Tomorrow, we're going to learn how to verify whether or not two equations that they give me are inverses of each other. We'll learn how to do that piece tomorrow, so don't do those homework problems yet. Let's do our last example together, example number 3. What kind of a shape would this make? That would make a parabola. Parabola looks a lot like what letter? Looks like a U. Would that pass a vertical line test?
Yes.
Yes. Would it pass a horizontal line test? No. To pass a horizontal line test, everywhere I put my pencil, it would have to cross in one and only one spot at a time. If I stop my pencil right here, do you see how it crosses twice? So this is a function because it passes the vertical line test. It is not one-to-one because it fails the vertical line test. So this is the kind of situation where we would need a restricted domain. I'm not going to go into talking about how to find that restriction right now. I just want to practice finding the inverse. So far, so good? What do I want to replace that function notation with? I don't like that. I can't do my next step if I have an f of x there.
Y.
Replace it with a y. Once I've replaced f of x with the letter y, then what can I do? Switch. What am I switching? The x and the y. So instead of y equals, it's going to be x equals. X equals what? Y squared. The squared stayed in the same spot, only the letter changed. Yep. Plus 2y plus 4. After I switch the x and the y, what's my goal now? Solve for y, get y by itself. So I'm looking on the side of the equation where y is. I want to get rid of that 4. How do I make the 4 cancel out? Subtract it from both sides. So I'm going to minus 4 from both sides. So now I've got this guy by itself. We are going to take that and we are going to complete the square. This is something that we did first semester. It's been a hot minute though. Let's talk about completing the square. I'm going to come off to the side over here and I'm going to draw a square. What do you know about all 4 sides on a square? They are all equal. They are all the same size. I'm going to put y squared up here. We are going through the process of completing the square. We practiced this first semester, but I know it's been a minute. I'm not going to expect you guys to complete the square on the homework, but I do want to practice it here. Yes, ma'am.
Why did we subtract 4?
Why did we subtract 4? Because our goal is to get y all by itself. I want to solve for y. I want to get y alone. So I need to get rid of all these pieces. The problem is that what I've got left here, they both have y's. One's a y squared and one's a 2y, so I can't combine them. I got to find some other way of getting them alone. So I put my y squared in this top box right here. I'm going to take that 2y and cut it in half. What's half of 2y? 1y. So 1y and 1y in each box. Y squared and 2y, is that what I have in the box over here if I put all those pieces back together? Yes. Y squared, 1y and 1y to get 2y. Is that box all the way filled in? No, we have to complete it. We are going to have to put a number down here in this bottom box. Here's how I figure out what that number is going to be. What do these two have in common? Y. So I bring that out front. What do these two have in common? Y. Remember, this is a square, so my two sides should be exactly the same size. Row times column. Y times what would give me 1y? 1. Y times 1 would give me 1y, so I have a 1 up here. That's a positive 1 because this is a positive 1y right here. This multiplied by this gives me 1y. What times y gives me 1y? 1. Positive 1. It's always going to be, guys, that I'm taking this number right here and pulling it out to the front. Whatever this number is, I'm going to pull that out. I want to look at another row times column here. What is 1 times 1? 1. So in that box, to complete my square, I need a number 1. If I add that to my box, I have to add that into my equation. So I'm adding a 1 right here. If I do it to one side, what do I have to do? Do it to the other side. So I have to add a 1 on the other side also. What is negative 4 plus 1? Negative 3. Look at the sides of the box. How big was this side of my square? Y plus 1. How big was the other side of my square? Y plus 1. So I have y plus 1 times another y plus 1. When I take something and multiply it by itself, that's the same as what? Squared. So this is y plus 1 quantity squared. So y plus 1 whole thing squared. How do I get rid of something that's been squared? Square root it. And if I do it to one side, have to do it to the other side. When we take a square root of both sides, we get both the positive and the negative. So I have to put a plus or minus here. The squared and the square root cancel each other out. So I have just y plus 1 left. How do I get rid of that 1? Subtract it. I subtract it to one side. If you do it to one side, you have to do it to the other side. Here it's going to cancel out. Over here, I do not have a like term that I can combine it with. So this is negative 1 plus or minus the square root of x minus 3. Very last thing I need to do I leave y in my final answer? No. What do I replace it with? F of x with that little negative 1. Replace it with your inverse function notation. Replace y with f inverse of x. I want to give you guys the remainder of the time to get started on your homework. I'll go over it with you, pull up some of the homework assignments, and I'll work through them with you, okay? Yes. Yep. The other one? Yep. Let me pop the homework up real quick so that everybody can grab a quick screenshot of it. Guys, if you want to get started on the homework and you want to work it out on paper first, these are the problem numbers from your book and the page numbers from your book that the homework is on. You will be submitting this on the McGraw-Hill site, which you can reach through Canvas. You can click on the homework there. All right, I'll pop this back up in just a moment, guys. You needed yesterday's, right?
Yes.
Okay.